Good afternoon, ladies and gentlemen. My name is Saurav Das. I work for the Open Networking Foundation, and I'm here to talk about an open source project that the ONF started earlier this year. So the ONF, as you know, is a standards body, but it also writes a lot of code itself, and I'm here to talk about one of our flagship projects. So you can see that Atrium, below it, it says it's an open SDN distribution. And I'll talk to you a little bit about what we mean and why we call it an SDN distribution. So why this project to start with? There's a lot of choices that you can see in SDN, right from the silicon layer down here that is available in hardware to the software that runs on top of that silicon inside the switch that provides a hardware abstraction for that switching chip. Then the box that gets built around all of this, and then the controllers that they talk to, right from the applications that run on the controller, and finally whatever orchestration management that you run on top of it. So there's a lot of choices in SDN. Some of it is proprietary, a lot of it is open source. And choice is a good thing because when you have choice, you also have, means that you also have competition. And when you have competition, it often leads to innovation. So choice is great. However, choice can also be very daunting for the end user. For an end user to come in and take something from each of these layers and try and put it together into a working solution, it's fairly challenging. And the ONF identified this earlier this year and said that, look, what we can do is that we can take the pain. We can take the pain of the integrating all of these open source components into a vertically integrated stack that we can package together and offer to the end user, that is the network operator, so that the network operator has something that they can get started with fairly easily, fairly quickly. So this is why we call this an SDN distribution. It's not just a controller, it's not just a switch, and not just an application. We have taken these and put it together and packaged it up and integrated it and verified that everything that we are putting together works together, right? So just like you go to a Linux distribution like Ubuntu or Fedora or Red Hat, they have done all the hard work of taking all of these open source pieces and putting it together and ensuring that it works. Same thing, we're doing this for SDN in Project Atrium. So the goals, like I said, we want to create vertically integrated stacks that all work together so we can enable network operators to download this distribution from one place and have it working and get started and up and running as fast as possible. Another thing we wanted to do was we wanted to have interchangeable parts in this distribution. We wanted to have the ability that you can swap out one part and slide in another part and it'll still work, right? And that means that we have to have this level of interoperability between the things that we put into this distribution. And finally, we want to work hand in hand with network operators to understand their use cases and have this distribution be part of the lab trials and possibly leading to field trials in order to give the network operators the confidence in SDN solutions. So what did we start with? And we started with something very simple. We said that the best way to give network operators confidence in SDN solutions was to give them something that they recognize and they work with on a daily basis. A simple router, right? A traditional router where you can configure VLANs on the interfaces, you can bring up BGP sessions with neighboring routers, and that router will forward traffic based on what it learns from the BGP sessions. So we did this by creating this vertically integrated stack. We started with bare metal hardware from the Open Compute project, and it's just white box hardware with no software in it. And then we put all this open source software into that bare metal hardware. You can get Open Network Linux from the OCP project. You can get OFDPA with which is something that Broadcom published on top of the Broadcom chips that you would often find inside this bare metal hardware. And then we put an OpenFlow agent on top of it so that it exposes OpenFlow 1.3 in all its multi-table glory inside the ASIC to an operating system, a network operating system like ONOS, which is also open source. And we wrote an application inside it. And then we hooked it up to Quagga, which is a BGP implementation. So all of this together behaves like a traditional router. And we have a bunch of partners that we work with. But we didn't stop there, because remember, one of the goals of Atrium was the ability to have interoperable and changeable parts. So the second thing that we did is that we also worked with a number of vendors. As you can see, they're all over here. A number of vendors that gave their vendor hardware and their OpenFlow implementation, and it still works with the same control plane software, the same ONOS controller, the same application, and Quagga on top of it. So this vertically integrated stack also behaves like a traditional router. And so we built 7 of these earlier this year. That was demonstrated in a conference in June. And even at the Layer 1 to 3 conference, if you step out to the ONF booth, you will see 4 of those hardware that have been arranged in a routed network. And each of these are talking BGP to each other, as well as to traditional routers. Now, I do want to spend a couple of minutes to talk about some of our technical contributions to this work. Now, it's really easy to say that you want to have interchangeable parts, but it's actually really difficult to do it in practice with OpenFlow supporting hardware. The reason is the old version of OpenFlow used to just have a single table in it, right? And that was easy, and everybody could do it, and everything was interoperable. But it didn't scale. And so people recognized that and went to a newer version of OpenFlow, where you just don't have a single forwarding table. You have control over multiple forwarding tables that you actually find in hardware that exists today, right? But the problem is that everyone has a different set of pipelines. All of these vendors, with their switching technologies inside, expose a different set of forwarding tables. And they're all valid OpenFlow tables, but they're all different. So how does a controller, any controller, like any OpenFlow controller like Ryu or OpenDaylight or ONOS, how can a controller manage all these differences between these pipelines? More importantly, how does an application written on top of the controller work with all of these differences? And so what we did is that we came up with an idea that we call flow objectives. And the idea over here is that you write the application only once, and you write it in a pipeline agnostic way. So it's not really aware of all of these differences. It only writes to this API. And then this API is implemented by a set of drivers that are actually pipeline aware. So the calls that the application makes then gets translated into the actual tables that go, that are under, the rules that are understood in the tables down in the switch. So think of it, again, a Linux analogy, right? A server operating system has a bunch of devices that connect to the computer, and the operating system talks to those devices via device drivers. Same concept over here. Network operating system talks to these equipment via a bunch of device drivers. I'm going to skip go very quickly through what that API looks like, and you'll see the need for it very quickly over here. And any router, you can imagine, has to filter. You can configure VLANs on those interfaces, and it'll only allow packets based on the VLANs and the IPs or the MAC addresses that you configure on those interfaces. So basically, it's a filtering operation. The problem is that different devices do filtering in different tables. So for example, the Corsa equipment over here filters MAC addresses on the first table, whereas the Broadcom chip filters MAC addresses on the third table. Now, an application shouldn't really have to care which table, what is going on. All it wants to say is that do this filtering, and then the driver actually puts it in the correct table. So this is a very simple example of how an application can be written in a pipeline agnostic way, and then the drivers take care of putting things in the right place. A similar example has to do with router send packet to the next hop. And when it sends packets to the next hop, it changes MAC addresses. It does a bunch of things before it sends the packet out. Well, different pipelines, again, do those bunch of things in different ways, but the application really doesn't have to care how it's being done. It just tells the Flow Objectives API that this is the next hop, and this is what I need you to do before you send the packet out to the next hop. And then it's up to the drivers to do those functions, and the application doesn't have to care exactly how it's done. So we've done some pre-release deployments. One of them was in Australia, where we worked with a carrier over there called RNet, and they put it one of our stacks in Sydney, and that peered, did BGP peering over the Pacific with another stack that was at ESNet in the Bay Area, in Sunnyvale in the Bay Area. and we exchange about 15,000 routes across the Pacific. Since the release, we are working with other network operators. Here's an example of how Bell Canada is trying this out in their labs and having that peer with one of their production networks. So this is still in the works. Here's an example how AT&T is trying it out in their Atlanta lab. And everyone's working with different equipment, and that's great because they have that choice of equipment, and everything is interoperable in Atrium. So AT&T is working with NoviFlow and Acton-based equipment in their lab. And we have a couple of other operators like DirecTV who are also trying it out. So far I've told you what is Atrium today and who's working with it. I just want to spend a couple of minutes telling you about what is coming next in Atrium, that is in the next release at the end of the year. So what's coming in the next release? Well, yes, we built a router in the first release, but there is a lot of work that remains. We do want to improve its performance. We want to make it more stable. And there are a few missing features that we do want to add to it. So improvements on the first release is definitely something that's coming in the second release. Again, interchangeable parts. We have worked with ONF in the first release, and there's a lot of work that is going on in porting whatever was there in the first release onto Open Daylight as well. So there's a couple of companies, Wipro and Criterion, who are part of the community contributors to this open source project. And they are also using the Flow Objectives API and the device drivers concept that we developed in ONOS, and that is being ported into Open Daylight as well. So this is going to be part of the B release. One final thing that's going to be part of the B release is a different use case. And this time, we're going to develop an open source leaf spine fabric for data center operations. And this leaf spine fabric, we have done some work before with ONLab and Dell networking. But now we're taking this concept and using the open source stack that we developed for switches, which is based on Open Network Linux and OFDPA from Broadcom. We're putting those into boxes from Acton and developing this leaf spine fabric for that purpose. This is an earlier demonstration where we had shown a 4x4 leaf spine fabric. This was with Dell equipment. We're doing the same thing now with bare metal Acton-based devices and Open Network Linux. This work is going to be part of AT&T's project with ONLab. You may have heard of it. It's called CORD, which stands for Central Office Reimagined as a Data Center. So that CORD work is actually much bigger than this. It's NFV plus SDN. So this will form the CORD fabric around which other things in CORD will be built, and that's slated for a field trial early next year. And now I'm going to spend the last few minutes just talking about a few other projects that are on the roadmap. It's really great when you start building these things in open source and you do these things in hardware and in scalable ways, then people come to you and bring you use cases. And these are a few projects that have been brought to us, and we are considering which ones we will tackle in the second half of next year. And so this is an interesting one. It comes from internet exchange providers. Now, internet exchange providers have these networks at various places all around the world. There are about 300 in the US, many more all around the world, where ISPs bring their routers so that they can eBGP peer across basically what is a layer 2 fabric. And there are very strict requirements for what this layer 2 fabric should and should not support, okay? And there are certain advantages of doing this in an SDN way as opposed to the way it is done with traditional networking today. So there are a number of IXPs that are interested in developing an SDN-based L2 internet exchange fabric. And so that's certainly under consideration. Here's the nice thing. Now I've shown you a single router, and I've also shown you that we're building a fabric. If you put these concepts together, what you eventually end up with is a chassis router. So instead of having a 40-port or a 48-port single switch under SDN control, take 6 of them, and then you can imagine that these 4 switches are the line cards of your chassis router, and these 2 back here are the fabric for your chassis router. And then your SDN controller with all the applications is really your controller card, also part of your chassis router. So this is, if you followed the work that Google and Facebook have done in their networks, this is essentially it. Google's Jupyter and Facebook's Six-Pack are essentially chassis routers built out of SDN technologies with bare metal hardware and the control plane pulled out of the switch. So this is something that definitely a few people are interested in. And once you build that, then it really opens up the floodgates, because you can think of a number of other applications. For example, this is something that the MEF have been, the ONF has been talking with the MEF about. Well, if you have these chassis-based routers, and you can build pseudo wires across it, well, then you can support Ethernet private line or Ethernet virtual private lines fairly easily across these chassis-based routers. Again, if you have the ability to build these chassis-based routers and you support an IGP as in addition to BGP, well, you can then start replacing your wide area network. And once you do that, you have the ability to add another global controller, for example, do traffic engineering on top of it. And this is what Google has done in its WAN network. So, and there are a few other people want to talk about packet optical, where not just the packet stuff is white box, but the optical stuff is also white box. There are some ideas around smart cities and IoT, and even enterprise networks that are completely L2 based. And so to summarize, I've talked about the goals of Project Atrium being integration, first and foremost, vertically integrated stack for a certain deployment or a certain use case, interoperability, interchangeable parts, and finally deployment. So the first release did bring together a bunch of things, both with white boxes and with vendor equipment. And we did that release a few months ago on June 30th. We built routers. We did some architectural contributions on flow objectives and device drivers. That's what made it interoperable across vendor pipelines from different vendor hardware. We've done some pre-release deployments, and there are more that are coming as we engage more operators. The B release will have the same thing built around open daylight, and will also include a different use case, which is the leaf spine fabric that AT&T is interested in as part of its core deployment. And there are many more projects in the horizon. So hopefully I've given you a taste of what the ONF is up to in the Atrium project. Thank you.
Excellent presentation. We do have 2 minutes, I guess, if you had a question. Do you have a question?
Hello, many thanks for all this information, insights. A kind of question regarding Atrium or the V release and OpenStack. I don't know if how you see the correlation. I don't know with the Neutron project.
That's right. So we are not targeting OpenStack right now because in the SDN stack, OpenStack would be at the very highest layer, which is the management layer. Or the orchestration layer, and kind of the use cases that we're looking at, we're first focusing on the lower layers first, the controller and the switch and the application, and then OpenStack comes into play. But we are not targeting that in April in this B release for Atrium. However, the B release will have that fabric that I talked about, the leaf spine fabric, and if you look at the work that ON Lab is doing in CORD, when you put more things around the fabric, one of the things that you put is that OpenStack integration. So CORD, which is also going to be all open source, will have OpenStack involvement, but not Atrium. Make sense?